Physical memory space has eclipsed raw processing power as the definitive bottleneck preventing the deployment of fully autonomous AI. When an AI model processes a long sequence, like reading an entire textbook or executing a multi-step autonomous agent, it must retain every previous step in its working memory to maintain context. In system architecture, we define this working memory as the key value, or KV, cache. This diagram illustrates the physical constraint. A standard 70 billion parameter model with a 32,000 token context window consumes roughly 80 gigabytes of VRAM strictly for this cache. That error represents a hard physical memory wall, making long context tasks mathematically impossible on standard local hardware. Google recently published a software-defined architecture called TurboQuant, designed to bypass these physical hardware constraints. Deconstructing the low-level mathematics of TurboQuant's extreme compression is the first step towards architecting infinite context agentic workflows locally. Systems engineers historically rely on a technique called vector quantization to shrink data and preserve memory. The structural flaw in legacy quantization is that it requires storing normalization metadata alongside the compressed data so the system can accurately decompress it later. Look at this abstraction. While core data shrinks, the required normalization metadata adds 1 to 2 bits of physical overhead per data block. At the massive scale of enterprise AI, this tiny recurring overhead compounds rapidly, neutralizing the initial memory savings. The first stage of Google's TurboQuant solution, PolarQuant, is engineered to eliminate this exact overhead. The algorithm achieves this through a specific mathematical pivot, shifting the data from a standard 3D Cartesian grid into a spherical polar coordinate system. Because the angular distributions of large language model data are highly predictable in this spherical space, the algorithm can safely discard the magnitude data. Dropping this magnitude data removes the need for per-block normalization, dropping metadata overhead to absolute zero. Changing the geometric shape of the data drastically reduces the memory footprint without deleting underlying intelligence. Discarding the magnitude data introduces a tiny residual bias into the model's memory. Google implemented stage 2 of the algorithm, the quantized Johnson-Lindenstrauss, commonly known as QJL. It acts as a highly efficient 1-bit mathematical error checker. This single-bit layer acts as a precision filter. It corrects the residual bias left over from the geometric transformation, ensuring accuracy without adding structural bulk. This data table illustrates the final benchmark results. For a 32,000 token context, the standard 16-bit cache requires 11.2 gigabytes of memory, while the TurboQuant 3-bit representation requires just 2.8 gigabytes. That yields an average 6-fold reduction in the total memory footprint. This extreme compression yields zero degradation in retrieval accuracy. In standardized tests like needle in a haystack, the compressed models achieved perfect scores. Operationally, the algorithm is data oblivious. It works out of the box and requires no expensive retraining or fine-tuning of the base model. When deployed on enterprise-grade hardware, this highly compressed data actually accelerates raw processing power. 4-bit TurboQuant delivers an 8x speedup in attention calculation on NVIDIA H100 architectures. Aggressively shrinking the data footprint directly amplifies processing speed. We can apply these enterprise-level mathematical breakthroughs directly to local, edge-level system architecture. Agentic workflows are AI systems designed to operate autonomously in continuous iterative loops, separate from single isolated prompts. These autonomous agents require massive, continuous context windows to remember their research, synthesis, and coding iterations over extended durations. Historically, running these looping agents locally on consumer GPUs guaranteed an instant out-of-memory error. A 6x reduction in the cache footprint alters the capabilities developers can access local unmanageable 12 gigabytes to just 2 gigabytes of VRAM. Developers use visual orchestration platforms like N8N to wire these autonomous agents together. This architecture map shows the new deployment reality. A local language model running via llama.cpp serves as the core, utilizing minimal VRAM thanks to TurboQuant. That central node connects via API to multiple interdependent agent nodes, handling research, synthesis, and coding directly inside the N8N environment. This setup bypasses the legacy requirement of paying exorbitant recurring memory taxes to cloud API providers to process long context operations. With this efficient cache compression, the local system easily runs infinitely looping autonomous tasks without hitting any physical hardware limits. Algorithmic compression decouples advanced autonomous agentic capabilities from the strict requirement of massive, expensive server hardware. The immediate economic reaction to the TurboQuant paper was severe. Memory semiconductor stocks dropped sharply upon publication. Investors assumed a linear relationship where 6 times more efficient AI models would cause tech giants to purchase 6 times fewer memory chips. That market assumption is a major architectural miscalculation, explained by an economic principle known as the Jevons paradox. The paradox states that when a resource becomes significantly cheaper and more efficient to use, total global demand for that resource increases. Dropping the inference memory cost makes continuous, local agentic workflows commercially viable for the very first time in history. Millions of local edge nodes will now deploy automated N8N workflows simultaneously, moving past the era of single giant models in a centralized data center. This explosion of decentralized, highly efficient deployments pushes total global hardware demand far past current projections. For developers and systems architects, the directive is clear. Do not blindly over-provision physical VRAM if software-defined compression can bridge the gap. Evaluate TurboQuant community implementations to optimize your local N8N agentic pipelines before investing capital into scaling up physical hardware. Engineering smarter mathematics to maximize existing hardware capacity is the most effective way to achieve true technological scale.